Okay, so hello everyone. Uh, Today we will discuss about electric flux and the theorem which is related to electric flux is the Gauss theorem. Okay. So the first question is electric flux. You see, electric flux is the total number of electric lines of force crossing the surface in a direction normal to the surface. Means this is the see, this is the electric field lines. Okay. And this is the surface. The electric field, these are the electric fields. The electric fields which are passing normally to the surface are called electric flux. So we can write the definition. The electric flux through a surface inside an electric field is the total number of electric field lines crossing the particular surface in a direction normal to the surface. In a direction normal to the surface. This is the surface, and the direction of the surface is this ds. If we consider this part, in this part, the direction of the surface is ds. Okay, and the electric field direction is e. This is ds. Okay, so surface in a direction normal to the surface. Okay, so it is the property of electric field. It is the electric flux is the property of electric field, and we represent this as a phi. Okay, so if we consider the electric flux of this smaller region is denoted as d phi. Okay, so d phi e is equals to how much? E into ds. Okay, e dot ds. Okay, means electric flux is denoted by E dot ds. Okay, so if we consider the dot product, then we know that vector multiplication is for two times. Multiplication is two types. One is dot product, and one is cross product. Okay, so dot product is A dot B, and the cross product is denoted as A cross B. Okay, so A dot B is A B cos theta, and A cross B is A B what sin theta. Okay, so this is the vector concept. Okay, so let's see. E is the vector quantity and ds is also the vector quantity. So E dot ds is the electric flux. Okay, so if we consider the electric flux through this surface is denoted as ds, and the electric field is E. So E dot ds is the flux. Okay, so now E dot ds is how much? E ds how much? Cos theta. Okay, so E cos theta into ds. Okay, so d phi is denoted as E n ds, where E n is the cos component of the electric field, E cos theta. Okay, fine. This is the format of electric flux. Fine, fine. If we consider, if we try to find the electric flux of that whole surface, then we'll just integrate it. Okay, so E phi E is integration of d phi E, which is equals to integration of this term, right? So integration of surface integration of E dot ds. Fine. So surface integration of E and ds. Fine. Now see, this surface is closed. So we will put the closed integration. Fine. Fine. Closed integration means the integration of the closed surface. So we'll put the integration symbol and the symbol of closed integration. Right? So this is the concept of electric flux. Okay. So now we will see the theorem, which is the Gauss theorem. Gauss theorem related to the electric flux. See, Gauss theorem. Gauss theorem. Okay. So let me first write the statement of the Gauss theorem. Statement. Right? The statement is saying the surface integral of electric field intensity over any closed hypothetical surface, which is called the Gaussian surface, in free space is equal to 1 by epsilon naught times the net charge enclosed within the surface. So let me write it first. The surface integration of, okay. So the statement is the surface integral of the electric field intensity over any surface which is closed hypothetical, means the Gaussian surface, in free space is equal to the 1 by epsilon times of the total charge, which is means by the net charge enclosed with the surface. Okay. So the statement is easy, right? See, the surface integral of electric field intensity over any surface. The surface integral, this is the surface integral of closed surface. So this is the surface integral of closed surface of electric field intensity over a closed surface. This is the closed surface. Okay, is equals to 1 by epsilon times of the net charge. Now see, E dot ds, surface integration of E dot ds. This is means nothing but the flux. Okay. So flux is equals to 1 by epsilon naught means q into q means q by epsilon. Okay. So we have to prove this. Now, write proof. This is the say this is the charge q, and we consider the hypothetical closed surface, okay, of radius r. Okay, fine. And the electric field is E. Fine. Means consider an isolated point charge which is plus q charge. This is the plus q charge of is put on the center of the sphere. Okay, center of the sphere of radius r, and the sphere is considered as the Gaussian surface. Fine. So the ds is denoted by this, and electric field is denoted by this. Fine. Okay, and the radius is r. Okay. So now see, we have to find the phi, right? We have to find the phi of the whole surface, right? Now see, if we consider the small amount of this closed surface, which is ds, so now we will find the electric flux of that surface. Okay, so electric flux of that small element surface is d phi e, which is equals to e dot ds. E dot ds, fine. Now E is electric field, so E is denoted as 1 by 4 pi epsilon naught Q by R square. Fine, fine. And see, E is in this direction, so we can put the R cap for the direction. Dot ds means ds and ds vector, so ds is also denoted in this direction, so we can put the n cap for the ds direction. Fine, so is equals to 1 by 4 pi epsilon naught q ds by r square, and the r cap dot n cap is the unit vector. Okay, so you can write r cap and n cap is the unit vector. R cap is the unit vector of what? Electric field, and n cap is the unit vector of what? The unit vector of the surface, right? If we find the dot product of two unit vector, how much? If we dot product unit vector, so 1 into 1, how much? Cos theta. Cos theta. Now see, cos theta. Theta is how much? Theta is 0. Na? ds is this direction, E is this direction. So theta is 0. Na? So 1 into 1 into cos 0 degree. And the cos 0 degree, the value of cos 0 degree is 1. So the 1. This is 1. Okay. So now 1 by 4 pi epsilon naught q ds by r square. Okay. Okay. So this clear? Now electric flux through the closed surface of the sphere. Just now we consider this is the sphere surface. Okay. So now the electric flux of the whole sphere is denoted as phi e, which is the surface integral of e dot ds. E dot ds. Okay. Now surface integral of 1 by 4 pi epsilon naught q by r square into ds. Fine. So 1 by 4 pi epsilon naught is constant. To put it outside of the integration, and the integration will be just for ds. Okay. Now see, this is the sphere, right? This is the sphere. So the integration will be how much? How much? 4 pi r square. Right? This is the sphere. So the integration will be 4 pi r square. Right? So now see, 4 pi will cancel. R square will cancel. Q by epsilon naught will be there. So we can write phi is Q by epsilon. Okay. So we can prove the Gauss theorem for spherical surface. If we consider the Gaussian surface is spherical, then we can prove like this way. Fine. Now see, if we the question is, if now I am not going to put the exact spherical surface, I am going to put the any surface, right? Any surface. And the Q is here and the any surface. So if we consider the any surface, then what will happen? The same. we'll put the small element which is ds, then the integration of surface integration of E dot ds, any closed surface, okay, which is not spherically symmetric, which is not spherically symmetric, okay. Then what will happen? So as per the formula, we can write surface integration of E dot ds is integration of E r dot n into ds. We can write, right, as per this. We can write now surface integration of E dot ds is equals to surface integration of 1 by 4 pi epsilon naught q by r square r dot n ds. Fine, fine. So q by 4 pi epsilon naught r cap dot n cap by r square into ds. Fine. Now this is the direction of electric field, means this is the unit vector of r cap and this is the unit vector of n cap, right? So r cap dot n cap. So r cap into n cap into cos theta will be there. So the value of r cap is 1, the value of n cap is 1, so cos theta will be there. So only cos theta will be there. Fine. So q by 4 pi epsilon naught surface integration of cos theta by r square into ds. Fine. Fine. Now see. Now the ds cos theta by r square. See, ds cos theta by r square is what? Ds cos theta by r square is du form, right? As per the solid angle concept, this is the du form, right? As per the solid angle concept, this is the du form. Okay, so this is the solid angle. Okay, and this is the r cap, this is the n cap, this is the theta. So, and the surface is this ds. So ds cos theta by r square is denoted as du form. Okay, right. So we can just replace it by ds cos theta by r square means du form. Okay. Now the integration will be for only du form, right? So in case of solid angle, the integration of du form will be what? 4 pi. So 4 pi cancel, q by epsilon naught will be there, and q by epsilon naught is what? Phi of e, which is equals to integration E dot ds. Okay, so you can prove this by any closed surface which is not symmetrical in size, and you can also put for the symmetrical size in this way. Okay, in case of non-symmetrical, then the concept of solid angle will be there. Solid angle will be there, and in case of just for the symmetric case, just the direct integration will be there, which is the, in case of sphere, the integration will be what? 4 pi r square. Right? So in your exam, you can prove it. I think if in the question paper, if the even means okay. So if okay, so proof of Gauss law for symmetrical closed surface, this is the proof. And for unsymmetrical closed surface, the proof of Gauss law is there. Okay, fine. So now move to the next part, which is the applications of Gauss theorem. Okay, applications of Gauss theorem. Applications of Gauss theorem. So we'll see some applications of Gauss theorem. So first application is number one is electric field intensity due to an infinite long state charge wire. Electric field intensity due to an infinite long state charge wire. Okay. So we have to find the electric field intensity for a long state charge wire. Okay. So this is the chart. So this is the wire. Fine. And this is infinite long. Okay. And this is charged. Okay. So we have to find the electric field intensity by using Gauss theorem. So this is easy. Let's see. So we'll consider a hypothetical surface of around this, right? This is the hypothetical. So let us assume a hypothetical surface of this portion of the infinite long straight line. See, we cannot find the electric field intensity for the infinite charge. Okay, so we will have to put the Gauss closed surface for a particular length, right? So see, this is for this region. We will consider a closed Gaussian surface, and there will be the shape will be what? Shape will be cylindrical shape, right? For the cylindrical shape, we know that there will be three surfaces. One is this surface, one is this surface, and one is this surface. Fine. And the electric fields are this way. Electric fields are this way. Okay. And now we consider the three small surfaces of this cylindrical shape. So this is the one DS surface. This is the second DS surface, and this is the third DS surface. Fine, fine. And the electric field is where? And the electric field is this way, right? E. This is the E. Fine. Now we have to find the electric field intensity of these three surfaces. Then if we just integrate, then we will find the flux. Fine. So now try. As per the Gauss theorem, we know the surface integral of E dot ds is q by epsilon naught. By using this formula, we can find the E, means electric field intensity. We can find. So now just put the three surfaces, which is the This is the first surface, this is the second surface, and this is the third small surface. Fine. So integration of E dot ds, this is for the first surface, plus integration of E dot ds, this is for the second surface, plus integration of E dot ds, this is for the third surface, and this will be equals to 1 by epsilon into q. Now see, 1 by epsilon into q means q by epsilon. Fine. Now see, like this is the state charge where, this is the state charge where, okay. So the total charge is q, the total charge, let me write, total charge is q, total charge is q, and the height is, for this particular person, the height is h. Now the linear charge density will be, linear charge density is lambda. Linear charge density means charge per unit length. Linear charge density means charge per unit length. Lambda is q by h. Fine. So q is how much? Lambda into h. Fine. Charge, see, this is the, see, this is h height, and the total charge is q. So linear charge density will be how much? Charge per unit height means q by height. Na? So now see, just integration of E, just put the integration E dot ds cos, see, for the first uh, small surface, see, ds is this side and E is also this side, means cos 0 degree, plus for the second surface, integration E ds cos, see, so for the second surface, ds is this side and E is this side, so this is the 90 degree, E ds cos 90 degree, plus for the third surface, E ds cos, for the third surface, ds is this side and this is the direction of, so this is 90 degree, 90 degree, is equals to, how much? See, q is replaced by lambda into h, so lambda into h by epsilon. Correct? Correct? Now cos 90 degree is how much? Cos 90 degree is how much? Cos 90 degree is 0. So this will be 0. Cos 90 degree will be 0. So this will be 0. Just cos 0 degree is 1. So we have just one integration, which is E ds into 1 means 1. E ds is equals to lambda h by epsilon naught. Just put the E outside of the integration. E ds is equals to lambda h by epsilon naught. Okay. So now we have to find the integration of this curved surface. This curved surface. Okay. This curved surface of the cylinder. So this will be how much? How much? E into how much? 2 pi r. 2 pi r h. Right. This is the curved surface. This is the h height, and this is the radius of r. So the integration of this will be 2 pi r h. Okay, and this is the lambda h by epsilon naught. Fine. So E will be how much? E will be 1 by 4 pi epsilon naught into 2 lambda by r. Right? Because see, E is equals to how much? E will be 1 by 2 pi epsilon naught lambda by r. Just put the 2 multiply in this side. So 1 by 4 pi epsilon naught 2 lambda by r. So this is the electric field intensity of the long, infinite long charged. Okay. Where lambda is what? Lambda is the linear charge density. Fine? Is it? Okay. So now the second part is electric field intensity due to charged thin spherical shell. Okay. Electric field intensity due to charged thin spherical shell. Okay. So this is the spherical shell. This is the charged spherical shell, and we have to find the electric field intensity. Fine. So let us consider a point P. Okay, and the direction of electric field is this way. Okay, and the direction of ds is also in this way. Fine. This is the center and the radius is r. Fine. So as per the formula of Gauss law, E dot ds, surface integration of E dot ds is equals to what? Q by epsilon naught. Okay, so surface integration of E, sorry, E ds cos will be 0 degree, ds and E in same direction, 0 degree, Q by epsilon naught. Okay, so E surface integration of ds is Q by epsilon naught because cos 0 degree is 1. Okay, so now just integrate it. Ds is how much? 4 pi r square. 4 pi r square is equals to Q by epsilon naught. Okay, see, this is the r and the total radius is smaller. Okay, this is the internal and this is the total radius is smaller. So 4 pi r square Q by epsilon naught. Fine. So E is 1 by 4 pi epsilon naught Q by r square. Okay, so this is the electric field at external point. This is the electric field intensity at the external of the ring. Okay. Okay. Now this is the outside of the cell, right? So this is the shell of radius r, and we consider the Gaussian surface of this, and we find out the electric field intensity of the outside of the ring, right? This is the ring. This is the ring of radius capital R, and we find the point electric field intensity at this point. Means this is the ring. This is the ring of radius capital R, and we consider this is the Gaussian surface, and we found the electric field intensity at this point, this position. Okay. So, and if we want to find at a point on the surface of the shell, if this is the shell, this is the thin shell, right? This is the thin shell, surface of the shell, and we have to find the in this position P. Then what will be there? R will be capital R. R will be capital R, right? And the E will be how much? 1 by 4 pi epsilon naught Q by 4 pi capital R square, right? Then in this case, this will be the radius of R, capital R, and the Gaussian surface will be this also. So R is equals to capital R. Okay, fine. Now, in case of if someone said to at a point inside the shell, this is the R inside the shell, then remember that the E dot ds, surface integration of E dot ds is equals to 0. In case of the spherical ring, there will be no electric field density inside the ring. Okay, so there is no electric field charge inside the spherical shell because there is no charge. See, the charge is distributed in the spherical in this, and there will be no charge in this portion. So the electric field intensity will be 0. So we can write E is 0 inside the shell. E is 1 by 4 pi epsilon naught, Q by 4 pi capital R square. This is in the surface of the sphere, and this is the outside of the sphere. Okay, clear? Clear? So we have discussed about the what is flux. Then we discussed about the Gauss theorem. Also discussed the proof of Gauss theorem, and then we saw the two cases where the Gauss theorem is applicable to find out the electric field intensity. Okay, so that's all for today. Thank you. Jai Hind.